Okay, we're going to look at current density estimation, but we're not really going to look at most of this. So we're going to talk generally about what's going on here. We're going to glaze over parametric density estimation because I don't know it. And then we're going to talk about non-parametric density estimation, which I understand a little better, but it's still really hazy. So we have continuous and discrete variables. And we can represent the probability with these equations here, where if you sum up these random variables and their probability function, you should get to one. You're either taking an integral or you're summing them up. Mm-hmm. And we're looking at different examples of continuous variables versus discrete. Mm-hmm. Density estimation allows us to learn about the shape of our data. I can start here. I think I'm less familiar with these points.
Yeah, I mean, I think it's just saying like, so basically what I was reading is that, you have all this data, right? And you can basically do like a nice little fit of it. So it's almost like like a linear regression kind of thing, but you're just like fitting a abnormal shape to it. So that allows you to see where there are a lot of points and where there aren't a lot of points. And so this kind of, I guess down here, you're looking at, is this like a typical data point, or is this abnormal point or outlier? So you can look at the density of the data and determine that.
Oh, I see.
Yeah.
Okay. That makes a lot of sense. Thank you. So I guess one obvious thing that's probably relevant for us is histograms. These are scores. So we have these statistics test scores. We have these linear algebra test scores. And then histogram just allows us to visualize the probability distribution of a continuous variable. And so what they do is they choose buckets and they throw, people's test scores into these individual buckets. And then the histogram represents that visually. And then we can try and look at it using like some 2D heat map, where we've compared the linear algebra score, some individuals' linear algebra score, and some individual statistics score. So this represents one person and both their scores. And we can see, I guess, as Nosa is saying, density estimation allows us to see what's more typical, right? We have some heat parts here, as opposed to what are more outliers. Like these are not what we would, I guess, primarily expect, or we would expect more people to fall into this category. So the parametric density estimation are models which can be described by a fixed number of parameters. Again, this is stuff that I'm a little bit less familiar with, but essentially we can use a single distribution to describe the density of these variables. Mm-hmm. Whereas non-parametric density estimation, it does not mean there's no parameters, but it means that these models can't be described by a fixed number of parameters. One can think of there are many parameters. So in this scenario, we have this histogram where these represent all the different points. So you can see that there's higher frequency in this individual bucket. And then you can use, this is actually kernel density estimator, where instead of like just taking one, let's say Bernoulli distribution or Gaussian distribution to represent this data, we're taking a lot and adding them to get this density estimate. So again, so another way to visualize that is the parametric case. We're showing this Gaussian. We're saying we're going to have one parametric model, and we're going to represent all the data using this one model, versus the non-parametric, which is saying that we're actually going to take several Gaussians. I'm assuming they're using Gaussian in this case. They might not be using a Gaussian, but we're going to take several models and scrunch them together, and so you get like more interesting shapes, right, than your just traditional three-dimensional Gaussian density, we're getting a density that is uglier. Similar things happening here, right? This would be our Gaussian scenario, whereas in this one, we're using
the kernels.
Yeah, I think we're using some type of kernel density estimation. And I'm going to assume they use the Gaussian here. So we have multiple Gaussians added together. So now we can talk about parametric density estimation. This requires a good background in, I guess, understanding probabilistic functions. And I don't have that. I don't have that. So
maximum likelihood.
Yeah, basically.
Yeah, dude, we talked about these.
I didn't do the homework.
Oh,
I don't have the time. It's hard enough just to finish the reading. So like, I mean, what I'm guessing here is that we're going to pick a model and we're going to tune the parameters to match the data that we're seeing, right? We get.
Well, we're not tuning them. We're optimizing for the maximum likelihood.
Okay, I see.
Yeah. So this theta, whatever the parameter is, theta is at the bottom here, is going to be the maximum of this log likelihood of p with that data that you have.
Oh, I see. So the way you determine your model, once you pick one, you determine some probability model. You use maximum likelihood estimator to determine the parameters of your model. Okay. So here's an example. Probability of theta landing on heads, bias coin. We get these flips. This is the data, D. We're going to say our model is going to be this. Does anyone know what the model is?
Bernoulli
Distribution, which is a discrete one. And then we're going to use the maximum likelihood estimator in order to, I guess, get these the way we want them. So here's the math. Maximize our likelihood with respect to theta.
Yeah.
All right. So, right, you can, similar thing with the Gaussian distribution, right? We have our probability distribution function. We need to estimate two sets of parameters. We're given this data D. And we want to get, I guess, the likelihood of getting some value x of I given, right, these parameters that are going to describe our Gaussian distribution. Here are the equations for the mean and variance.
Yeah, I think I think what it might be saying there is that you, like, if you ended up doing it, if you ended up doing the MLE, yeah, I don't know exactly what this is saying, but I think it's saying if you end up doing the maximum likelihood estimation, you would get those values that it's given, that are given there from mu and theta, or the equations basically that are given from mu and theta down here. And here it's just showing the method. So here first you maximize with respect to mu. Yeah, okay. So it's doing both actually. Take derivative with respect to mu and theta, or not theta, sigma.
Sigma squared.
Sigma squared, yeah. Okay.
Interesting choice.
And then here are and so here are the equations now. So you end up with that it's just the mean, the MLE of the mean is, or the parameter mean is just the mean of the data, and then the sigma squared is just the sigma squared of the data, if you do the math.
Oh, I see. And that's just an artifact of the way the Gaussian distribution is defined.
An artifact, what do you mean by that?
Like, it's designed such that when you, I guess, finding the model,
finding the parameters
for the model, Well,
So what's happening here is like you're given some set of data. You've like pulled some data. You have the data, and now you want to fit a Gaussian distribution to it.
yes.
And you have these parameters that you need to figure out what they are. And saying the way that you figure them out is just use the maximum likelihood estimation, and then you can solve for what they need to be.
Right, but I guess I'm saying that as compared to the Bernoulli
Mm-hmm.
one was really ugly. Like you had to derive your equation in order to determine, and I'm not sure what the language is here, the parameter of your model,
Mm-hmm.
right? Here, if you're doing a Gaussian distribution, it's actually pretty straightforward. If you want to determine the parameters of your model, you find the mean and the standard deviation, the mean and the variance.
Those are the parameters, right?
Yes.
Okay. I don't understand the difference that you're drawing out between the two. It's the same thing. It's the same thing. It's just a different distributions, right? So in the first one, you assume the Bernoulli distribution, which only had one parameter, theta. But in the second one, you assume the Gaussian distribution that had two parameters that you need to figure out, mu and sigma.
I guess this seems much more familiar to me. Like I think that's an equation we have, as opposed to deriving the
So you
equation.
see down here the what is it? Sigma, um, not sigma, theta. Damn, theta MLE is just the mean of the data.
Oh, I see.
So like yeah, it's familiar to you because like you kind of just like know these things like, oh, like, yeah, obviously the mean is this, obviously uh the deviation of data is this, but like this is like sort of a formal way of doing it. If you didn't know what the if you only knew the distribution but you didn't really know how to figure out what the parameters actually are.
I see. So MLE is just a more robust way in case we have different kinds of distributions.
Yeah.
Okay. Um, so I guess you would use those equations to determine your Gaussian density in this example.
Mhm.
Right. Okay. Um, I guess this is probably the more interesting one if you're familiar with um, maximum likelihood estimation, which is non-parametric density estimation. Madi notes that it's useful for visualization, classification, and regression. A 1D histogram, I guess we'll start there. It's one of the simplest non-parametric. Given some density, we're going to split it into, I guess, I'm not sure why it says 0 to 1. We're going to split it into bins, where I guess there's given m bins, we can split it into the bins using this equation, um, and you simply count up the number of points. And so when you want to find the probability of x to be in a certain bin, you just take the number of points in bin C and divide it by the total number of data points times the bin width, which is 1 over m.
Okay. So that would be the probability density function for the data.
Let's see. Um,
Okay. I mean, it makes sense. Like the probability that X amount of points are in this bin are going to be the total number of points in the bin. Yeah.
yeah, I guess for some random variable x, the odds of it being in, let's say, bin C2 is just going to be the number of points in bin C2.
Oh, I see. I see. Okay, got it.
And so once you sum up all the probabilities, you should get to 1, right?
Yeah.
And that's what this is. I think this is what that's trying to show.
Got it.
Right. So it should be greater than or equal to 0. And when you sum them up, the probability densities, I guess the density P of X, you should get to 1. I guess this is the mathematical proof that that's the case. Do y'all mind if we
we can skip that.
Okay. But like that's cool if you want like really discrete stuff, but what if you want well, I think I actually misunderstood this. What if we want the density of both of these, right? You have 2 dimensions instead of just, this was a 1D case we did here. So given n samples, you split it into n bins, the bin size is h. And for the 2-dimensional, we'll have just 2 different, let's see. If we're doing the same bin size for both, m equals 10, then we end up with 100 different bins. And we visualize that this way.
I see.
So this is a way to use the histogram to visualize the density of our data in 2 dimensions.
Got it.
And the output depends on where you put the bins. So your choice of bin width and like, yeah, I guess where you put the bins is going to determine the output, which kind of sucks. So if you were to slightly change this, okay, bin width breaks at number 0 and 5, bin width 0.5, versus same bin width, but now you have the breaks at different points, you know, with this different histogram. So it's really sensitive to like where you put it, which kind of sucks. I guess that's that for the histogram stuff. Are there questions there? Also note that these dots at the bottom represent the data points. Okay, so kernel density estimation is kind of like histogram, but what's going to happen is, oh man, you know what? There was such a beautiful, did y'all look at the visualization thing that the person did?
Yeah, I did.
Oh my God, it was so beautiful. I wonder if that would be useful here.
I mean, it takes a while to like, you know, or I guess you just scroll down. Yeah.
Yeah. And then, yeah, basically, maybe I'll come back to this. So what's happening here is we're going to have a kernel density estimator, where 1 over h is our bin size, right? The distance that we're looking at, and then k is our
kernel,
our kernel function, such that k must be greater than or equal to 0. K of u must be greater than or equal to 0. The summation of it must be 1. I'm not sure what this identity means or this one. But what we can do is we can have different models as our kernels. So before we talked about, we showed the 1 Gaussian versus if we did, let's say 2 Gaussians. Here, right?
Yeah.
1, where this might be multiple Gaussians. So in that case, our kernel function would be a Gaussian kernel. And
wait, can I look at that equation really quickly again? UKU equals 0.
Do you know what u might be?
Well, it seems like just the input of k. So it's saying that whatever the input is times the kernel should be 0.
I guess when you sum them up all together, it should equal to 0.
Oh, when you sum them up, okay. The inputs in. Okay, I'll just take the. And then this xi minus x. So this is xi is all the points, you sum through all the points, and then x is just the data point that you're looking at. Okay.
I think this is the distance to some point, and you normalize it by the distance. So for each point you're looking at, you want to compute the distance to all the other points,
Right.
and then you normalize that distance by your smoothness factor.
Your smoothness
And
factor.
that's your input
I thought you
to.
said that was the number of bins.
Yeah, but I think the word we use for this is going to be, I think the word is smoothness factor, because that parameter determines how smooth your stuff is going to be.
Okay.
So I think we should go back to, I think we'll come back to why H is important.
Okay.
For now, we're going to focus on the K. So for kernel density estimators, we choose a kernel function. So here's an example of using a Gaussian, but you could use other types of density estimators, like a top hat. This one was the one used in the visualization. I think it is. It's a Russian last name. Or, you can use exponential, linear, cosine. You have lots of options. And then what you do is you're going to apply your kernel function to the data, and it's going to normalize it by your smoothness factor H. So that's going to tell you like how wide your bin is essentially. And you apply this over each data point. So we're looking at this data point. It gets this, I think in this scenario, it's a Gaussian, or this one of those. And or you look at this one, okay, this one's slightly next to it, right? So you can see all the different kernel functions over each data point with some dimension H across. And so when we sum those together, we end up with this density estimate of all the data. As opposed to, you could try and do this with one big Gaussian, right? But using kernel density estimator, now we've summed up all these different kernel functions into one density estimate.
Okay.
Okay, so yeah, this is the effect of kernel bandwidth. This is the H. I guess bandwidth is the word they're using here, right? So this is an H of 1. So the, I guess the bin size, I think that's the way I think about it, is pretty small here. And so you get these really sharp points of the data. Whereas as you increase bin size, now it becomes more smooth, right? If you have a really large bin size, so you can see how wide these distributions are, it gets even more smooth until the point where it's almost useless. Like, you want to be able to like get the right bin size such that it adequately represents the density of your data set, without being like overly narrow. So like here we get this peak here, but that doesn't really represent the data.
Yeah.
Or like overly smooth, where like we have one big peak, but that doesn't really correspond that well to this.
Yeah, that makes sense. Okay.
So here's the data points here. We have 50 data points. We could use the histogram, and we just have a frequency. So this is, if we use this, or we could create 200 uniform points to have a smoother density function, or you can simply implement this on each data point. So we could do 200 different points, and then we have, I guess, a smoother density function, or we could just put it on each. I don't think I actually understand this very well.
I think they're calculating the kernels. Yeah, so go up one, let's see. Yeah, so they're trying to calculate the kernels. So first they do the 200 uniform points. And then for each linearly spaced line, let's calculate a Gaussian kernel over the given 50 points. And so you have one of these for each 50 points. Seems
So let's
like.
calculate the Gaussian kernel over a given. I think no, they discretized it to 200, and then for each linear space line, they calculate a Gaussian kernel. So the Gaussian kernel is calculated for each line,
Oh,
and
I
it
see.
uses all the 50 points.
Oh, I see.
Gaussian.
I see. That makes sense.
So, as an example of kernel heights for line at 0, linear space points, I guess these are the linear space points, 200 by 50. 50 points, 200 linear space lines. Here's the 0 point, right? Negative 15 to 15. Negative 15 to 15, here's the 0 point. And then for each one, let's say we look at 0, density at L equals 0, B of X equals 0, mean equals L equals 0. We apply the kernel, or hold up. We're doing the mean of L0, where L0.
That makes sense. That's the kernel. Yeah.
I guess this is the kernel function K.
Yeah.
But then we also have 1 over H.
Yeah, so like bandwidth, kind of like normalization thing.
Yeah.
Okay.
So based on the Gaussian kernel estimator, once we
do it all, right?
Yeah, end up with this.
Okay. Makes sense.
And then they have MATLAB code that does this.
Okay.
Look at this.
No.
Neither do I.
Okay.
So, but they implemented it, and now we have the true PDF.
Okay.
So what kind of kernel did they use here?
Silverman.
Using the Gaussian kernel, a good choice for is, a way to pick your H.
Oh, I see.
This value. So they did this. Let's calculate the kernel density for each linear space point over 200 given data points.
Oh, okay. Wait, so what's the true PDF? Scroll down. Exponential. Oh, okay. So they just got a Gaussian for each of those areas. 2 pi. Yeah, so I think they just took a normal distribution on the first one, normal distribution on the second one, and then you just took the mean of those distributions.
Oh no, I just divide by 2 because we're adding density value 2 times.
Yeah,
okay.
So the mean, right?
I guess so. But I guess like because they knew it was a normal distribution, right? Because they randomly did points from normal. This is the true probability density function.
Oh, okay, yeah.
Of the data.
Yeah.
But then they did a Gaussian kernel density. So this one isn't normal. They're using a Gaussian model for the kernel.
Okay.
They loop over 200, one size x of 1. Okay, they say they calculate u, which is the distance from this point to all the other points. Okay, I see. They do the kernel version of that. And then they divide that by h. Take the mean. Huh. Okay, looking at the code actually was helpful. I feel so much more confident trying to implement this. Okay. Ben, you awake?
Yeah, I'm here.
Okay.
All right. Let's keep going. So I guess again, I think choosing the kernel bandwidth, there's a rule of thumb. You're probably use this if we're going to use a Gaussian kernel. I think most people are going to use a Gaussian kernel. I guess there's a more computationally intensive approach. Split the data in 2 sets, kernel density estimate for the first, measure the likelihood of the second set, repeat over many random splits and averages. Oh, I think that's you can use the estimation maximization function to determine a good H, right? Where you take a guess. No, maybe I'm making stuff up. But I know one of these is connected to EM somehow.
Okay.
Measure the likelihood of the second set.
Yeah, I mean that seems
an average.
That seems sort of like a expectation maximization thing.
Yeah.
What's M? M is the number of data points?
No, I think M was the total number of bins, right?
I think you're right. Well, N was the number of.
Because the example above was like multi-dimensional.
No, it's the number of data points, because go up in the code, it says numel data, right? And when you're calculating H,
Yeah.
I think numel gives you the number of points, right?
Yeah, I think you're right.
Oh, okay.
Okay. I mean, it's a pretty simple concept.
The concept's easy, and I guess looking at the code, it's not that complex to put into practice either.
Yeah. So if we look at the true probability or the true density function and the so what's the takeaway from this what's the takeaway from this?
Yeah, what's actually useful about this? Is it just another way to visualize data?
I think it shows that you have to be smart about choosing your kernel estimator, perhaps. Like you could.
I guess I'm struggling to understand because if you already know your PDF, you can just integrate your PDF to get like your cumulative density function.
But the idea here is that you don't know what it is.
Oh, you don't know what it is.
Yeah.
But you're
so I think it's maybe showing that there's some variation between the actual PDF and what you get from
the approximated.
Yeah, the kernel density estimation. But if you don't actually know what your PDF is, it gets like at least a shape, you know.
Oh, okay.
I see.
Yeah, and the further you increase your bandwidth, like the more certain you are of the data, then you can kind of get closer to the true PDF.
I don't think that.
Or increase or decrease, I'm not sure which one it is.
Well, I guess maybe this is trying to show us that using Silverman's rule of thumb, even if you use like a not that great, like if you use that for your bin size, you can get a decent job done.
I see. Yeah.
Maybe that's the point here. Because I think getting the bin size right is one of the hard parts of kernel density estimation.
Yeah, that makes sense.
But this kind of sucks, right? Like this, there's a lot more likelihood to get these values. I don't know what to think about this either. But I think the point is, if you're able to so the example they used was, yeah, I guess the point is to try and use KDE so you can start to have some predictive power for new data. I think that's the point. I'm willing to bet this is going to come up again, and we are going to really hope we really understood this. But we'll see.
Fingers crossed it doesn't. Yeah.
Well, that's what the homework's for.
You said what?
I said that's what the homework is for.
I guess. Yeah. Should we stop recording?
All right.